I can use this, right? Okay.
Yeah. If you just
Yes.
do that.
Okay. Sounds good.
So what I do is I give you 3 minutes. I'll give you a 3-minute one. So that you perfect.
Sounds good.
Okay, let's get started. Whoever is still outside can come in for the neutrino session. And we're going to get started with Rui, who's going to be telling us about self-engineered neutrinos in light of large structure data. Go ahead.
Okay. Hello, everyone. Okay, it's working. Yeah. Okay. So, hi, everyone. Today, I would like to introduce this work where we probe the neutrino self-interactions through large-scale structure data. And this work is mainly done by Adam He, who is a PhD student at USC. And talking about neutrino self-interactions, the motivations to include such new self-interactions include explaining the origin of neutrino mass and connections to dark matter candidates, and also addressing some problems in particle physics or the cosmology, like hypertension. And in our work, we consider the flavor universal scenarios where neutrino self-interactions is mediated by this massive scalar, which corresponds to this green curve. And in these scenarios, we have a Fermi-like self-coupling constant, G effective, that describes the full Fermi interaction. On the right plot, I show the ratio of the neutrino self-interaction rates over the Hubble expansion rate. And if this rate goes below 1, then the neutrino starts to free stream. And we can see that in the standard cosmology, where neutrinos only have weak interactions, the neutrino free streaming happens at the onset of BBN. And if we include these neutrino self-interactions, we can see the neutrino free streaming is delayed. And this delayed neutrino free streaming will leave imprints on cosmological observables such as CMB and the matter power spectrum. So let's say its effect on the cosmic microwave background first. So after neutrino decoupling, so in the standard scenario, so free streaming neutrinos travel through the photon-bearing plasma at early times, and gravitationally pulling the photon-bearing wavefront slightly ahead of where it would be in the absence of neutrinos. Thus, this free streaming neutrino will lead to a phase shift in the CMB power spectrum towards larger scales and a slight suppression of its amplitude. And we already know that neutrino self-interactions will delay the time at which neutrino begins to free stream. Thus, it will shift the comparing to the standard model, it will shift the CMB power spectrum peaks towards smaller scales and boost their fluctuation amplitude, as shown in the left plot. And the another interesting effect is on the matter power spectrum. In this plot, we show the ratio of the linear matter power spectrum with respect to the standard one in the lambda CDM model, and we can see that neutrino self-interaction leads to affect the matter power spectrum in a scale-dependent way. This is mainly due to its impact on the gravitational potential. And we can see that for the larger K, the modes enter the horizon before neutrino decoupling, it leads to a suppression of matter power spectrum. If it goes to larger scale, for the modes enter the horizon during the neutrino decoupling, it shows a bump-like feature. So of course, for the even larger scales, it behaves exactly like the standard lambda CDM model. So, and if we decrease the value of the strength of neutrino self-interaction, it will lead to an earlier onset of neutrino free streaming, which will shift this bound-like feature towards to smaller scales. So this dependent modifications to the power spectrum can be probed by different large-scale structure probes. And then here I listed the large-scale structure probes we used in this work, and also the corresponding scales probed by these measurements. First is the BOSS full-shape galaxy clustering data, and the second one is the Llama alpha forest measurements. Here in this work, we used compressed version of likelihood presented as a Gaussian prior or model-independent amplitude and slope of the power spectrum at a pivot redshift around 3, and also this scale around 1. And the third measurement is the weakling data from DES year 3. And note that here we also use Gaussian prior on S8 parameter in this work. In this work, we also first use this effective theory of large-scale structure to model the nonlinear power spectrum for the first time within this neutrino self-interacting cosmology, and as introduced by Professor Ivanov yesterday. And the left plot shows our key results. We can it shows the 1D posterior probability distribution on the interacting strength G effective within our baseline model. In this model, we just we vary the another 2 free parameters. One is the self-interacting strength, and the other one is the sum of neutrino mass, in addition to the 6 standard cosmological parameters. And also note that in this work, we fixed the effective number of neutrinos to its standard value. And if we see the Planck-only result, we can say that it has two modes. One corresponds to the weakly interacting modes, which is close to the standard model. And the other one is this small bump. It corresponds to this strongly interacting modes with a delayed onset of neutrino free streaming over here. And this bimodality mainly comes from multi-parameter degeneracy with this G effective parameter, and the related parameter include that the angular size of sound horizon and the fluctuation amplitude and the spectral index. And we can see that if we see this solid line, if we include this large-scale structure measurements, we can see the weakly interacting mode is like ruled out, and only this strongly interacting mode exists. So then we compare the minimal value of chi-square within this modes with respect to that of lambda CDM model and this extended lambda CDM model with additional parameter, the sum of neutrino mass, and we found a huge difference, like around like minus 30, which corresponds to preference at like 5 sigma level. It shows that this full data set, namely CMB plus large scale structure, strongly favors the presence of a strong neutrino self-interaction compared to the standard cosmology. And this table will also show the breakdown of the chi-square contributions from each data set. We can see that this preference is mainly driven by this Llama alpha forest measurement and slightly by this DES measurements. So this preference can be understood in the context of the modifications to the linear matter power spectrum. Here, on the left plot, we show the ratio of the linear matter power spectrum over the best fit power spectrum from a Planck-only analysis of lambda CDM model. And this green curve corresponds to the best fit neutrino self-interacting model from this our full data analysis. And this orange and the blue curve correspond curves corresponds to smaller couplings, and this black curve corresponds to the best fit extended lambda CDM model from the full data analysis. And we also, from previous analysis, we know that the llama alpha measurements are more sensitive to the slope of the power spectrum around this scale compared to the amplitude. So on the right plot here, we show the slope of the power spectrum for these models, and this data point shows corresponds to the shows the slope measurements derived from llama alpha forest measurements with 2 sigma uncertainty, and we can see that neutrino our best fit neutrino self-interacting model can lead to a suppression on this slope of the power spectrum, better fitting the llama alpha forest measurements. On the other hand, the suppression of the beta power spectrum at smaller scales also mildly favored by the weak lensing measurements from DES. So, and then we just also looked into these 2 observational tensions in our work. One is the asset tension between the measurements from CMB and large-scale structure, and the H0 tension between CMB and local measurements. And when if neutrino decoupling delayed until close to recombination, it will lead to reduce the sound horizon prior recombination, which may be able to solve this H0 tension. And also the resulting suppression of the metal power spectrum at smaller scales may be able to solve this S8 tension. So in this plot, we show this 2D posterior distribution for the parameters of interest. We can see if we focus on this purple versus this red distribution, this purple one is the full data analysis of self-interacting neutrinos, and this red one is the full data analysis of this extended lambda CDM model. And we can see that first, the neutrino self-interaction can erase this H0 tension between the full data analysis and the local measurements. And it also happens in the asset tension scenarios. It can erase this asset tension between this full data analysis and the DES measurements. Just note that in this full data analysis, we also include the asset prior from DES. So to fully understand this asset tension within this cosmology, we need to present a more careful analysis. And also interesting, we can, within this neutrino self-interaction model, we also found that there is a 3.5 sigma preference for non-zero sum of neutrino masses. So this message is at the level of like 0.3 eV, which is also consistent with the previous bounds from neutrino oscillation experiments and also from the previous Planck bounds. And in the last slide, I just listed the key findings in this work, and of course, given the effects from the neutrino self-interactions on the cosmology, like its effects on the sound horizon, and also its effects on the matter perturbations, we of course expect that this neutrino self-interaction to be further exploited with the next generation of spectroscopic surveys, and we hope we can get more information about this beyond standard model physics from these upcoming measurements. Thank you.
Thank you, Rui. Do we have questions from the audience? You have time for a couple.
So the 5 sigma evidence is mainly driven by the Lyman alpha, the negative like 26 out of the 28 chi-squared was there, right?
Right.
So do you know where that's coming from? Why is the Lyman alpha disagreeing, so much with the standard picture and giving you evidence for this new neutrino interaction?
So as shown in this plot, this llama alpha measurements here. So in the previous work, with they present the llama alpha first measurements. They found that this llama alpha measurement is more sensitive to the slope of the matter power spectrum around this around 1 h/meg/sec, and also we found that combined with the other best fit cosmological parameters, and we found that within this model it can show this suppress the slope of the matter power spectrum. So that's why it's better fit this llama alpha measurements compared to this lambda CDR model.
Okay, so you're saying the Lyman alpha power spectrum slope is preferred to be much different from the other guys?
Yeah, from the amplitude measurements.
Okay.
Simon has a question.
Just a small comment. So the interaction strength that you're finding is very, very strong, which means that it suggests that there is another light particle around that couples to the neutrinos, and so it might be worth in follow-up work to float delta ineffective as well, because it might contribute, it might affect that, including that particle explicitly in your fit might be helpful, perhaps. Just something to think about going forward.
Thank you for the comments. Thank you.
Okay, very quick.
Yeah, thanks for the nice talk. Maybe just a very quick follow-up on Simon's question. I think I have the same feeling that the self-interaction you're finding is quite high. Have you considered other constraints from either like colliders or ice cube or whatever? Do people already place bounds for the self-interactions of neutrinos, or is not as competitive?
Thanks for the questions. So in this work, we didn't, but we also compared our constraints on G effective with the previous bounds from lab experiments, and we found that it may be in tension with that bound. But if we consider like tau flavor neutrinos, it may be consistent with that bound.
I see. Thanks.
Okay, let's move on. Any other questions can be asked later in private. So next up, Rui, can you stop sharing your screen? And then Yusen, you can go ahead and share yours.
Yeah. Yes. Okay.
So what we're going to be hearing about now is Higgs and neutrino hierarchy problems in relation to Lasker structure. Please go ahead, Yusen.
Yeah, thank you. Thank you for having me here. So in this talk, I'm going to quickly review some of the large-scale structure signals on some particle physics models that people have been thinking for a long time. So none of those are my models. My job is only to connect those, dig out what's the cosmological data. But there are indeed some examples that the two things can closely relate to each other. Sorry, I thought okay, maybe so I should do the...
Yeah, just do it like that.
Oh,
do you have like in preview?
I probably have... Oh, no, I should have. Sorry.
Oh, whatever, present it with
Yeah.
Okay.
Yes.
It's a bug with Keynote app. No, yeah. So stop to share.
Oh, yeah. Sorry. Let's share again.
Preview. This one. Full screen.
Yes. Here we go. Yes. Okay. Good. So, and the point is to show that many of the dark sector cosmology that people have been working on is cool, and they show the powerfulness of the cosmological observation on this pretty isolated physics, only couple mainly to gravity, but they actually have real applications for the physics that people have been thinking about. Especially, so we already have some examples like connecting the energy, like a cosmological survey that usually happens around the EV or 0.1 EV scale to some interesting inflationary physics that can leave the perturbation to the observable on the scale. But the thing is that if you ask most of the particle physicists, we are working on a pretty low energy experiments like LHC, right? So it's like 100 GeV, 10 TeV scale. So the question is that is there any relation or any motivated scenarios, even just figure out some examples that these two scale physics on the two scales actually relate to each other. Okay. So I'm just going to use the three examples to quickly give you some ideas like that this can happen. It's a short talk, so don't worry, I will only just give you a brief idea. So I will talk about the scenario called the mirror twins model and also unnaturalness model, which are the models that people wrote down trying to address the Higgs hierarchy problem. And I'm going to discuss what are the dark sector signals will come from this. And also talk about the idea of the majoron, which will relate to the physics of the Snell model neutrino decay and can again imprint some interesting power spectrum for the signal. Okay, so let's start from the twin Higgs model. This is the model that written by people trying to explain the Higgs hierarchy problem by push up the new physics scale, the scale, energy scale when the new physics need to show up to 10 TeV scale. And you can see we are just trying to avoid the LHC constraint as much as possible because we haven't seen anything so far. But the idea is that you use a mirror symmetry to postulate a whole set of the Snell model-like particles with very well-defined coupling and the particle spectrum and mass, so that they can run inside the loop corrections to the Higgs mass and cancel the divergence, and then so that you don't worry about the problem until a much higher scale. It's good to avoid the LHC constraint because all these new particles you're adding, they don't carry hour gauge symmetry interactions. So basically it's very hard to see them. But then the question is that if the model is so well, how am I going to see any signals of this model, or it's just writing it down for fun? Okay. So actually, this idea actually have a kind of automatically tells you that there will be a bunch of dark sector particles that you have in the late time universe, much later time scale. For example, because there's a mirror symmetry, so you expect to have free streaming radiation like neutrinos. You have interacting radiation like mirror photons interact with your mirror baryons, have dark acoustic oscillation physics. And then after the recombination, the sector, they become free streaming. So there are lots of dynamics in this setup. And because of the motivation for solving the Higgs hierarchy problem is actually give you a more well-defined mass spectrum and interactions so that it's not just random. And in the end, it's fits by some parameters and which I'm going to, I mean, if you're interested, I can tell you more about this. So it's true, there are already cosmological constraints that you can put on this model on the three parameters that actually sets everything, all the dark sector ingredients and energy density. And you can even just examine how good or how natural this model would be in terms of solving the hierarchy problem. Basically, this quantity is a ratio of the electroweak symmetry breaking between the mirror sector and our sector. Basically, if the larger the number is, the worse the performance of the model. So if you want the model to work as what we want to solve the hierarchy problem, you want this number to be below 5 or something. So you already see like cosmology actually put a pretty strong constraint on this. There are also applications to the H0 and S-state tension, but I will leave that afterwards. As I mentioned, in this sector, you have very interesting dark acoustic oscillation features, and then you again see Francis' name show up again. So if you take a matter power spectrum, for now linear calculation, so it's ideal work. With and without the dynamics in this the dark sector, you get this suppression and then also oscillation features. And each of these features, if we get to measure it, they will together fix all the 3 parameters of this model that address the Higgs hierarchy problem, and even can provide you some cross-check to see if the model is the thing that solve the issue. But of course, we all know that there can be a severe nonlinear corrections, so we don't necessarily get to see all these scales in the oscillation features. So this is just our little attempts of doing some gauge simulation, dark matter only, trying to figure out the smearing of these oscillation peaks. So definitely, if you do that for today, you don't see anything, but at the higher redshifts, you may have a chance to see something. So that's, and you also see a similar thing when we're trying to do this, translate this into the 2-point correlation function of the cosmic shear perturbation for the trying to apply for the DS year 3 data. You can again see the suppression of the features, that non-trivial feature that you can have on acoustic oscillation. But that's okay. I think we just need to think harder and then see if we can really have probably a higher redshift measurement. Of course, there would be all the issues, the galaxy bias and stuff, but eventually, if we get to have a power to identify this physics, we actually learn a lot for the high energy scale stuff. Very quickly, another example of solving the Higgs hierarchy problem people also talk about is this unnaturalness model. I have to say, even among particle physicists, we are semi-crazy, but we also think this model can be even more contrived because there are lots of things you need to put in. But still, it's an interesting idea to think about the hierarchy problem, and it can still be true because we don't have much clue at the moment. So the basic idea is that you imagine you have a large n copies of the Snell model sectors exist, which the only difference that you have is this Higgs parameter, Higgs square, Higgs mass parameter that go all the way from a negative large number to a positive large number, where the number roughly correspond to the scale when the new physics should show up. And our Snell model sector live around in the middle, which is a much lower energy scale. And this is not from some entropic selection. This is from the fact that if you have a particle that decay reheat into the universe that we live in today, if this reheating particle is not too heavy, it will prefer to decay into lighter sectors, and which is our sector. So that's why our energy got populated. If you want to push the new physics scale to the 10 TeV, then you need this 10 to the 4 sectors. But in the end, only a few around us will be populated. But in terms of cosmology, what it gives you is just some dark sectors with a tower of warm dark matter particles, which are the neutrinos in other sectors, which has some well-defined mass spectrum and the temperature, or if you specify your model. And again, the existing data can already constrain such a model with the horizontal axis is the energy scale of the particle that reheat into our universe in terms of GeV. And the vertical axis, again, is how much tuning that you need in this model. So if the number is 1, then it's very natural, you don't need any tuning. If the number is small, that means even after doing all this work, the model doesn't perform well. And cosmology is, again, the only way that you can set constraints on these dark sector models and the solution. So for some examples, if your neutrino mass is Majorana, it already sets a very strong constraint and to disfavor the model. In terms of the large scale structure signals, matter power spectrum signals, when you have multiple warm dark maters that got non-relativistic at the different times, it's going to change the shape of the power spectrum separation. So these vertical lines just indicated the inverse of the co-moving time when each mode becomes non-relativistic, and it's going to change that shape. So that you will get a separation that looks quite different from a single warm dark matter. I let you to pick the mass and the temperature, trying to match the energy density today and ineffective in the early time. You have a chance to still see the difference. So again, if we have a more precise power spectrum measurement, we may be able to, of course, constrain the model, but also have the chance to tell the difference between this separation of the matter power spectrum. Okay. So the last example I'll talk about is a different hierarchy problem, which is trying to explain why the neutrino mass is so much lighter than all the other fermions. And again, it's an idea that has been there for a long time. So the idea is that, it can be that the neutrino just get a mass from a different spontaneous symmetry breaking comparing to the Higgs mass. So you have additional field that gets a VAV and media to us, so you have a much smaller mass. But the outcome of this is that the Goldstone boson of the symmetry breaking actually can induce the neutrino to decay. So you can imagine if I have a heavier neutrino can decay into, maybe the lightest one is massless, so it can decay into totally dark radiation, and you can estimate the lifetime or decay rate for the example I put in. So comparable to the age of the universe when the mass generation scale of the neutrino is of 10 to the 5 GeV. And there's no other way that you can constrain any of the terrestrial experiment. So once you open up the possibility that our neutrino may have a finite lifetime, you need to recast the bound on the neutrino mass, because now you can have much heavier neutrino, but decayed so that it looks like the energy budget in the neutrino is lower. So here we recast the bound using the 2018 data, and you can take a look afterwards. In terms of the matter power spectrum, the neutrino decay will changes the redshift dependence of the structure formation. So the black curve here is if I assume a stable neutrino with a given mass. So here I assume 0.25 eV just to illustrate the point. If the neutrino decayed, you have less warm dark matter in the early universe, so it stops suppress the power spectrum as much as a stable neutrino. So there's a difference, but you will say that if I do see a power spectrum like this, power spectrum ratio like this, how do I know this is from a stable neutrino or a heavier neutrino that decay at earlier time? Yes, okay. So that turns out that the way to break the degeneracy is that maybe if you can get to see a slightly higher redshift perturbation, then you have a chance to break degeneracy. And that's why we use Euclid data trying to do a forecast and to say that you can actually have close contours of the neutrino mass and lifetime in some examples. So I'm out of time. I will just leave this slide here. Yeah, thank you.
Thank you, Yusen. Are there one or two quick questions from the audience?
Hey, Yushin, thanks for the talk. It's really nice. I will make it really quick. So I realize I think N-naturalist, the point of N-naturalist is dominantly reheating to standard model sector, and the other sectors are subdominant. But I feel like your bound relies on all the other sectors will contribute significantly to the total energy, right?
Oh, no, it
So-
actually doesn't have that much. So it's actually, even though a little bit, that's already changes the cosmology quite a bit. So here we didn't try to crank up anything. We really just use the best scenario they want,
Okay.
but you still have branching ratio into other sectors. And that's the warm dark matter and radiation that would give you the signal.
what's, for example, how much contribution you get from this to dark matter, omega matter?
For the exact number, I don't remember. For the radiation, you can still easily get like a 10% level
I see.
compared to the photon, and then yeah.
Okay, cool. Yeah, we can talk more
Yeah,
later.
we can talk.
Yeah, thanks.
Okay, let's postpone any other questions to later.
Yes.
And switch speaker again.
Thank you.
For self-interacting neutrinos in large-scale structure, part 2.
Do I need to put this back?
So I'll give you 5 minutes and a 3-minute one.
Sure. Thank you.
Okay, David, when you're ready, get started.
Okay, well, thank you so much as the organizers for organizing this nice workshop. Today, I would like to present some results and some analysis we have done regarding self-interacting neutrinos, as well with the large-scale structure observation that we have today. This is a work I have done in collaboration with Francis Yancy Racine and Joe Hotteling from the University of New Mexico. So I'm just gonna flash this slide. Neutrino cosmology is a very important branch, right? We can study the fundamental properties of neutrino using cosmological observation data. And in particular, we are putting a lot of effort on trying to constrain the mass of neutrino, as you can see in this forecast analysis for megamapper and other observations, right? But actually, cosmological observations can also help us to constrain other fundamental properties of neutrino. And one of these fundamental properties that's important to constrain is this prediction of the standard model. So the standard model predicts that neutrinos should decouple from the thermal bath, more or less when the universe is around 1 MeV. So it's more or less after 1 second of the Big Bang, right? And this is something that we can calculate just taking into account the weak interaction and how the Hubble rate evolved at very early times. This has very important implications for cosmology because this implies that at the very early universe, before recombination, neutrinos were the only radiation species that were free streaming, right? So all this has very significant impact in the evolution of cosmological perturbation. So what we can do is go to our cosmological data and try to test this fundamental prediction of the standard model, right? And this is something that people have been doing for a while. The most simple scenario that you can imagine to alter the free streaming of neutrino is assume self-interactions. This is an analysis coming from the 2013, so more or less like a decade ago, right? In which they found that the CMB observations were actually consistent with 2 different pictures. So on the left-hand side, you have the regime that will correspond to the standard model limit, in which neutrinos are not interacting or interacting with the weak interaction, right, as we expect from standard model. And on this right-hand side, you have a mode in which neutrinos are strongly interacting among themselves. So CMB is telling you that you can have these self-interactions in the neutrino sector using this particular model, which is the most simple approximation that you can take in cosmology. So, of course, this is something that has been done or observed in other analyses, something that we have been observing consistently for a decade or more than a decade right now. Just to flash another results as well. So this analysis on the left, you have an analysis coming from the Atacama telescope data, where they have found actually that the preference for this self-interacting neutrino is really high. And as you know as well from Ruiz's talk, is that if you include the Lima alpha forest observation in this, you also have very high significance for this strong interaction neutrino, right? But the thing is, so more or less all this story has been constructing around the CMB observation, right? But now we have observations coming from the large-scale structure. We have the galaxy power spectrum, and we can use that data to try to constrain this self-interaction. And actually, this is something important because this kind of model predict master cluster suppression at very modest scales, right? This is something that actually can add as well as the suppression that you expect seeing from massive neutrinos, right? So Thanks to a lot of people in this room, we can use now effective field theory of large-scale structure and go there and test the data. So this is what we have done in a CN-dependent way without assuming anything or any data coming from the CMB. We test this model using galaxy power spectrum. And this is the result that we got. On the left, you have basically this is a profile likelihood in which you can see the strong interacting mode is actually fit a little bit better data than the typical standard limit. And this is just a Bayesian analysis considering different combination of data. And more or less is always the same story, right? The strong mode provides a better fit to the cosmological data. And again, this is independent of the CMB, just using the galaxy power spectrum data. So if you are not surprised, I was surprised at the time when I saw this analysis. So because you don't expect to see this without CMB. And actually, if you compare the phenomenology of two models of the two different analyses, the CMB analysis and the large-scale structure analysis, you will see that the phenomenology is more or less the same. What you are getting is a suppression of the primordial amplitude of the power spectrum, as well as a change on the tilt of the primordial power spectrum. So because of that degeneracy with these parameters, you can get away with this strong interaction among neutrinos, right? So the phenomenology is more or less the same. So you can imagine now, the question is, can we fit CMB and the galaxy power spectrum at the same time using this particular model? And unfortunately, it's very difficult. So using this particular representation, which is the simplest representation you can imagine for self-interacting neutrinos in cosmology, basically a mechanism to delay the free streaming of neutrino, is difficult to fit the data here. As you can see, the dashed black lines represent the analysis coming from CMB and BAO, and the red one is when you combine CMB with the galaxy power spectrum. And yeah, the statistical significance is very small, although it's difficult to capture this model. So using nested sampling or whatever algorithm that you are using is difficult actually to capture very precisely the statistical significance of this model. But in general, you expect to see that it is very small. So this analysis disfavors this particular representation that, again, is the simplest representation that you can imagine for cosmology. So that was our reaction at the time. And if you are wondering why it's difficult to fit both data, it's basically somehow touch on the sigma A tension. So basically, because you have this mild discrepancy between a large-scale structure and CMB data, right? You cannot get away with this suppression of the fluctuation of the amplitude of the power spectrum. So here there is a profile likelihood analysis color-coded. The yellowish colors are the values that we expect to see in the CDM, and these purplish colors are the ones that you expect, but you need actually to fit CMB and large-scale structure data. If you don't include the polarization data, you will see that you can get away with the suppression, and actually the strong interacting mode provide a slightly better fit to the data. But once you include the polarization, which is the one that can actually constrain or break the degeneracy between AS and tau, it's difficult to get away with this. So you don't, the preference for the strong mode goes away, basically. So we now have observed, independent of the CMB, that this kind of feature is also there in the data, in the galaxy power spectrum data, although it's difficult to fit both the CMB and the large-scale structure data with this particular model. But it's something that I would like to highlight here is that this cool hint that there is a yet to be discovered feature in the early universe. This might be that the model we are using is the wrong model, or is too simplistic to represent the real feature in the data. And of course, this motivates the construction of more complex models, both in cosmology as well as particle physics. And something that also I would like to mention is that it is important to bear in mind that these really complicated and not standard scenarios can also, at some point, or could provide a good fit to the data. So we have discussed, or a lot of people have discussed here, that it is difficult to go beyond from the lambda CDM picture in the case, for example, of the effective field theory of large-scale structure, because all the framework we have construct is just basically relying on lambda CDM and a few other approximations. But it's important to bear in mind that this kind of physics could be there, so we have to be aware of that. Well, that's it. Thank you.
Thank you very much, David. Are there any questions for David? Okay, then let me ask. So your work is kind of similar to Rui's work. Do you, like, in light of your work, I think the main difference is that Rui and company included DES data, DES and Lyman alpha data.
Yeah.
You didn't. So in light of this, do you think that's the main tension? Should that be done or not? What's your statement there?
Well, the main difference is that our analysis, I would say, is a little bit more conservative. We don't use the llama alpha forest data. And actually, as Rui said, the thing that drives this 5 sigma preference that they are seeing is actually driven by the llama alpha forest data. So our analysis is a little bit more conservative.
Okay, thanks. And Rui, do you agree with that? Good. And very, very quick while Kaio is sitting up.
Thanks for the talk. So if I understand correctly, your evidence for the strong interaction is coming from this lower sigma that you get from the full shape, right? Do I get that right?
Yeah, actually it's a lower amplitude. It doesn't
Lower
reflect in the sigma as a lower sigma.
I was asking because, you know, this lower amplitude you are getting with this code that you're using is not there in other codes analysis of the same data set. And this is an issue, I guess, which, you know, people have been discussing for a long time. It's part of all this priors effect and whatnot. What I'm trying to say is that, you know, if like this discrepancy in the amplitude that you see, it's not there, for example, with PyBird, another code from my
I see.
group, right? So, I mean, it's important that we keep this in mind.
Okay, well, thank you for the comment.
Okay, thank you very much. Let's switch speakers. Thanks, David. And Kaio will now give a talk on neutrino winds.
Is it working?
Okay,
All right.
looks good. Go ahead.
Okay, yeah, thank you very much. It's a pleasure to be here. Today I'm going to be talking about some work of mine on like different ways of extracting neutrino masses from large-scale structure. And yeah, this is work of my advisor, Marino Rovede. How do I go? Nice. Okay, yeah. So it's 5 p.m. I'm just going to skip this. Let me just like very briefly motivate all of this. We know that neutrinos are massive, and we know that that's the case from oscillation experiments. And LBNL is really like at the forefront of this program. Just wanted to mention that. And what we are currently doing is yes, we're essentially like on a hunt for the neutrino mass scale. So we have some current constraints from like, we know like there's a lower bound for oscillation experiments. Some of the masses have to be larger than 0.06 eV. We also have this result from laboratory experiments, namely Catherine, that they're like a weighted sum of the masses. That should be like a weighted average. That should be smaller than a 0.8 eV. This is like a laboratory constraint. And we also have, of course, cosmological constraints, which is the thing we're mostly interested about. And then from Planck 2018, this upper bound to the sum of those masses is like 0.12 eV, or like taking into account this first year release of the DESI data, it's like a 0.07. And the point is that this is more stringent. All of those constraints are more stringent than the laboratory experiments, but they are not really like as robust because there are some other dependencies, there's stress of priors and so on. But still, cosmology is a great way of probing this. And another point is that it's important to keep in mind that neutrino mass really is like BSM physics. This may be super exciting in the sense that this might be connected to like new forces, new interactions, and we can learn a lot about the universe from neutrino masses. But this also may be just, I don't know, there's some right-handed neutrinos there, and it may not be as exciting as like some other scenarios. Yeah, and what neutrinos do in cosmology is they just free stream over cosmological distances. So when neutrinos become non-relativistic, they give like a 0.5% contribution to the matter budget. And they have some large thermal velocity, so like on the order of like 15 kilometers per second. And what that does is just prevents neutrinos from clustering on scales below the distance they travel, which is like around 20 megaparsec for like a 0.1 MeV neutrino. And the reason for this, as I have this cartoon here, is just because this acts like escape velocity that really prevents them from clustering on those small scales. And then at the level of the matter power spectrum, this was all already mentioned by previous people talking about neutrinos, but what happens is there's a suppression of power on small scales, and this is what we're hoping to measure in the future. And it's very important to emphasize that like this is really great. This is going to allow us to, hopefully it's going to allow us to detect the neutrino mass scale in the upcoming decade with the upcoming surveys. And I would also like to stress that in order to carry out this program and make sure that we are ready to actually obtain a neutrino mass measurement in the future, we need to make sure that we are computing our observables both accurately and efficiently. And this is something that I've been working on for the past few years. And also, like, we should all care about this. It's really important. Like, at the very least, we're setting some very clear targets for laboratory experiments. But there's many other reasons why a detection or a non-detection will have like very stringent cosmological implications. So this is really important. However, this free streaming suppression is not really perfect. And the reason for that is that there is some degeneracy with a number of things. So like a dynamical dark energy, which is very popular nowadays, is something that produces similar signatures. You can change the power spectra. Or if you have like warm dark matter, things like that, it can also like suppress your power. And there's also like, because it's a small scale signal, there's some sensitivity to the modeling of nonlinear scales, which is, we know it's complicated. And yeah, this is all to say that we should be looking for new ideas as well and new ways of probing neutrinos from future surveys. And then what I'm going to talk about today specifically is this idea of neutrino winds. And the basic picture here is that because of the peculiar motion of halos, the neutrinos are going to have some like local dipole distortion to it. So it's kind of like neutrinos, they preferentially cluster behind a moving halo. And that's what this plot shows. There's some like a number of interesting things, a number of interesting observables that derive from this. So one is like a dynamical friction effect. And this is really just because neutrinos are accumulating behind the moving halo. So there's like a net exchange of momenta between the halo and the neutrinos, which essentially just causes the halos to slow down. This is a plot of just the fractional decrease in the velocity of those halos as a function of mass. I won't go into any of the details of this, because what I'm primarily more interested about and what I think is more exciting is really like this dipole distortion. And the idea here is that there's a local CDM neutrino cross correlation. So the cross correlation between the CDMs and neutrinos is going to be modulated by the long wavelength relative velocity. So that's what's going on really. So this is really like a 3-point function. And another way to think about this is that you have to stack your 2-point function like against the relative velocity in order to extract this signal. What I'm plotting here is that in practice, what that means is that you should expect to find some offset to this peak of the CDM new cross correlation along the direction that's parallel to this relative velocity field. And yeah, we're looking at this in simulations right now, and we're very excited about this. But I told you this is like a 3-point function. You can go to Fourier space and like study what this bispectrum signal looks like. On the left there, I have just like a plot of like, what is this bispectrum shape? And as you can see, just like peaks in the squeeze limit, where the long mode is much smaller than the short modes. And also something that to keep in mind is that there is like a parity odd under like this flip between the CDM and neutrinos. And the reason for that is that if you flip the two, you flip the relative velocity as well. So this is important. And there's also like just to get some idea for what the amplitude of this bispectrum is, because it picks at the squeeze limit, you can do a comparison to like local non-Gaussianity, but just a rough comparison, not to be taken too seriously. But this kind of like gives you some taste of what the amplitude is as well. And then for real surveys, there's some complications because we don't measure the neutrinos directly, of course. We just measure like the galaxy and the matter field. So what we have to do is really like cross-correlate. You have to consider like 3-point cross-correlations of the galaxy and the matter in order to extract the signal efficiently. I'm running out of time and it's already 5 p.m. So I don't want to go into too much details on this. Yeah, but the point is that this has some interesting features. So for example, you could potentially open a window into the mass splittings because the signal here is goes like neutrino mesh to the third power as opposed to neutrino mesh to the first power, which is the traditional scaling of like the dependency of neutrino mesh on cosmology. However, this is really, really challenging. Like it would take something like 1 billion galaxies to detect this effect, assuming like the minimal mass from oscillations. Of course, if it's a mass that's slightly larger than the minimal mass, the prospects are much better because of this fast scaling, but it would be really challenging to measure this. And we essentially want like as many galaxies as possible in the local universe because this has some redshift scaling, which favors like a Z of 0. So yeah, but it's very exciting. And I don't know, this is a potential way of probing neutrinos that's completely different than traditional methods based on just the free streaming, which is great as well. So yeah. Yeah, and then to conclude, we know the neutrinos are massive, and we have cosmological and laboratory experiments with such complementary constraints. And then, yeah, what neutrinos do in cosmology is that they just suppress power on the small scales, and this is really great. Hopefully, we're going to be able to measure the neutrino mass scale from this in the upcoming decade, and this is something I'm looking forward to for sure. But there's also this effect that neutrinos accumulate downstream of moving halos forming wakes, and this is a completely independent proof of neutrino masses that can potentially be detected by future surveys. So yeah, this is very exciting. Thank you.
Thanks, Kaio. Are there any questions?
Thanks, Kaio. So from your scaling that you were showing, so if I have like a 3%, 5% warm dark matter, would this be detectable then? Because, it's like 10 times more than infraction than neutrinos, right? Could I detect that? Would I still need like 1 billion galaxies? Can I get away with,
I see.
like 50 million galaxies?
Yeah.
Or because, my question is, if I raise the fraction, if this is a thermal relic, I also lower the free streaming scale.
Exactly.
Right? So,
yeah,
so where's the trade-off?
That's a very good question. Yeah. So the problem here is something that I did not mention at all, is that this is all limited by the free streaming scale. So if you push the free streaming scale to lower values, you're essentially running into trouble. You have no effect. And the reason for that is that we want halos should be moving over scales where the neutrinos is really like isotropic. So there's a homogeneous sea of neutrinos. And yeah, that's like a big problem in trying to extend this to different scenarios, is making sure that you do have a hierarchy of scales, that your free streaming scale is much larger than the scale of like halos, or like the scale of non-linearities, which is like the typical distance that these halos are traveling. So yeah, ideally we want to model build our array around like increasing the fractional contribution of the component to the density, but at the same time keeping this hierarchy of scales, and this can be challenging.
Thanks.
Okay, thanks, Kaio. Xuheng, we're right there. You are. Gonna swap speakers, and now gonna have self-interacting neutrinos in Lastre structure part 3.
So hi everyone. Today I want to talk about a very different regime that you can probe with large-scale structure, also as a neutrino self-interaction. I'm Xuheng from Johns Hopkins, and this is with David and Sajid. So just want to briefly motivate the work. We know the standard model is not complete, and we have this neutrino portal, which is a normalizable extension of the standard model, one of the 3 portals we have. However, the light particle that it couples to neutrino are really poorly constrained. Let's see why. Let's say we plug in the number of the constraint from the fact that neutrino is not free streaming. If the coupling is stronger than this, found this is a very large number. And this is why is that? Because when we are looking for long-range interactions for standard model particles, we really benefit from the fact that you have coherently enhance the effect for larger number of particles by considering our objects. However, it's very hard to achieve such large enhancement from the neutrinos in the lab. If you look at the hard collisions, it's just simply not that efficient when probing this parameter space. And the solution we come up with is instead we can look for these long-range interactions in cosmology, which can benefit from the fact that they have a huge number of neutrinos. Let's take a look at a very tall example. Let's take a look at the cosmic neutrino background in the Milky Way. We know the temperature of the neutrinos today, and the Jeans criterion says the gas gonna collapse in they're gonna collapse into form bound states if the gravity pressure induced gravity is stronger than the thermal pressure. And you can just plug in a number for a sphere that is comparative size of the Milky Way and found that for cosmic neutrino background, this is simply not true. The thermal pressure is much larger than the gravitational the pressure induced by the gravity. This is, of course, trivially true. We know that neutrino is free streaming today. But however, this is not true if you change this into, if you add new long-range forces. And because it's such weakly constrained, you can check that if you add long-range force that is 10 to 6 times gravity, you will trigger Jeans instability in this system. And here's the general statement about this work, which is just saying that nonlinear neutrinos, but nonlinear bound state of a neutrino can form if the neutrino couples too strongly to gravity. And here's a very simple model setup we have, which is just a Yukawa force. We tune the parameter space such that the mass of the scalar field is ultralight. And we also set the interaction range to be extremely small such that we can avoid all the early universe constraints. And because such system is too simple, it's very simple, and the people have studied in the past, there's a well-defined background evolution equation, there's well-defined linear perturbation evolution equation we have. And we also found analytic solutions assuming that neutrino is a fluid. We also have a modified version of class, which we can trace the exact evolution of the whole system. In both of the cases, we found that if you have if neutrino couples to force that is much stronger than gravity, you can produce, you can have very enhanced perturbation growth at some time in the universe. And we interpret this as a formation of nonlinear structures. So here's take a zoom-in look of the perturbation evolution. Under the fluid approximation, this is how the perturbation equation looks like. Because of this new long-range force, you're going to have this extra red term that is added to your equation motion. And because this depends on how large it couples to this new force, if this new force is too much stronger than gravity, this red term is going to dominate in your equation motion. And just to give a sense how quick, and this can get you a very fast growing mode of these perturbations, just to give you a sense of how large it can be, if you plug in G prime is 10 to the 4 times gravity, then you get something like 8 to the 10. So this is much faster than the standard model perturbation growth. And we found that the perturbation of neutrinos can grow to order 1 within 1.5 Hubble time. This is also very scale dependent. As you vary the K from within the interaction range to outside interaction range, you can see this rapid perturbation growth is exponentially suppressed. And we can interpret this as a peaked structure formation at the range that is comparable to this interaction range. And if you solve the previous equation motion, here's typically what you're going to find. At large scales, that is larger than the interaction range, the perturbation growth is suppressed simply because it's outside the interaction range. And at a smaller scale, you are suppressed by free streaming. So only in between these two scales, you can have a very significant perturbation growth. And can evaluate how much fraction of these are forming halo based on press-Schechter formalism, and found that this can jump from 0 to 1 at the range that is corresponding to the interaction range of this new force. And that's why, based on this, we assume that the structure will form at the size that is corresponding to the radius of the interaction. Then we scan the parameter space, starting from for the parameters, we evolved the linear perturbations theory, and we found where the neutrino perturbation is nonlinear. Then we see, we assume there's a structure formation by that time. And we can find these very significant structure growth from neutrinos. Depending on your model parameter, they can form up to 10 to 15 solar mass, and they can form at redshift from 0 to 100. But this doesn't, of course, this is very different from what you expected from the standard model. But however, neutrino is only 0.5% of the matter, so it does not necessarily mean they are ruled out. But however, people have studied a similar system in the past for primordial black hole. And indeed, people found that even with a very small abundance of primordial black hole, you can enhance the structure formation significantly. And these are usually parameterized by the Poisson noise. We found these neutrino halos are very similar to primordial black hole at large scales. I mean, their gravitational effect. They are bounded system with a finite size. They are still effective point mass at the scale which we are observing larger scale structure. We also assume that these distributions are uncorrelated at the scale that is larger than interaction range, simply because their interaction range is the force is exponentially suppressed at the because the Yukawa force is exponentially suppressed. And we can evaluate the matter power spectrum expected from these neutrino halos. And we sum up the contributions from dark matter and the contributions from neutrinos. And we found this very significant enhancement of matter power spectrum. Here we are fixing the mass of the neutrino halo to be 10 to the 13 solar mass and vary the time when they form. And you might wonder why you expect order 1 effect on the matter power spectrum, even though the neutrino is only 0.5% of matter. This is because the matter power spectrum cares about the combination of your density and your perturbation. And if neutrino forms nonlinear objects at early universe, the combination of these can be comparable to what you expected from the cold dark matter. And you can already see from this plot, if you form this object at too early, at a very high redshift, you'll be ruled out by the observations. And combined with the predictions of this halo formation, we can put a constraint on the neutrino long-range self-interactions. And we found that up to 10 to the 4 times gravity can be ruled out at a very long range. And that's all. So there's a potential cleaning argument in the DESI area, which is if we can actually observe the cosmic neutrino background by observing the free streaming effect of neutrinos, that might indicate that all these physics that are producing non-free streaming neutrino can be ruled out.
Thank you very much for this great talk. And any questions from the audience? Back there.
Can you show the constraint plot again? Like, I mean, why can't you go to higher coupling? Like, it seems like you pick out like a very special set of couplings.
Yes, yes. So if you continue to go to higher coupling, there's another effect I haven't talked about, which is the background effect. That is saying the wave are going to be sourced by the background neutrinos, such that it changes the mass of neutrino in the universe. And if you suppress the neutrino mass, they become more and more relativistic, and such that you cannot form bound states.
Okay, one last question on the other side.
Yeah, I'm just wondering, like, for neutrinos to be coherent, do we also need neutrino to be very cold, or is really just 1/n5, or we also need neutrino momentum to be very small?
So if the neutrino is relativistic, there's suppressions, because when it's relativistic, the suppression are strongly coupled to the phi. And also at when they are very hot, they also have effective mass from you can just see them from the equation. But yes, indeed, I think the phi itself, the phi sector is still very cold. And I don't expect the thermal correction from it. So just in terms of this parameter, just in terms of quantum correction from this, if you set the cutoff to be the mass of neutrinos, this is at the borderline. Because both, yes, indeed, this is a very light regime, but this is also very weakly coupled.
Okay, I think any follow-up can be discussed offline. There were also a few kind of other questions that I had to cut off. So those can be kind of asked later or tomorrow. And so with that, let's thank all speakers from the session again. And then I guess we continue tomorrow morning at 8:30, I believe.